On the first day of this unit, we looked at the composition of electromagnetic radiation. We said that it consisted of an electric field wave, a magnetic field wave, perpendicular to each other, and perpendicular to the wave travels. Electromagnetic radiation is a wave. Now, we also addressed 4 different observations, 4 different properties of waves that are exhibited by electromagnetic radiation that support that notion that EMR is a wave. One of them was polarization. Remember, that's the one where we turned the polarizing filters and we ended up filtering out all of the light. The polarization was a property of waves. It's exhibited by EMR. Diffraction, the spreading out of a wave when it goes through an opening. That's a property of a wave. It's exhibited by EMR. Interference, when a crest hits a crest or a crest hits a trough and so on, constructive and destructive interference. That's a property of a wave, and that's exhibited by EMR. The 4th one was called refraction. Refraction was the bending of a wave, and we talked about that a little bit in Physics 20. We reviewed it very, very briefly on that first day of the unit, but we didn't go into detail about it. Today we're going to go into detail about refraction. Just to refresh your memory, though, I'll give you the analogy that I gave you on that first day of this unit. We have a parking lot. The parking lot is made out of pavement. Beside the parking lot, you've got a swamp. So over here, pavement. Over here, you got a swamp. You've got soldiers marching in the parking lot. Okay, you got 6 soldiers here. If we look at these soldiers from above, it looks like a wave front, the crest of a wave. Now, zoom forward a couple seconds. These soldiers are going to be not in the same place because they're marching. You got a couple soldiers, though, that have entered the swamp. But what happens to these soldiers as they enter the swamp, besides the fact that they get wet? Yeah, they're going to slow down. So now if we're looking at these soldiers from above, now the so-called wave front looks like this. Let's zoom forward another couple seconds. Okay, soldiers up here. Hey, this guy's just getting ready to enter the swamp. This guy's well into the swamp. This guy still is. This guy still is. Starts looking like this. The wave front, if we think of it that way, was going directly to the north. Now the wave front is going over here northeast some way. The wave bent. The wave bent. Why? Because the speed of the wave changed. That's what happens in refraction. When a wave enters a new material, when it goes from pavement to swamp, or when you're talking about light or EMR, when it goes from air to glass, okay, the light changes speed. And as a result of the speed changing, then the direction will also change. Now, what else changes? We got speed changing. We got direction changing. What else we got changing? The wavelength. Look at this. Hey, look how far apart they are here, and look how close they are together here. The wavelength will also change. So, goes to a new medium. That causes the speed to change. That causes the wavelength to change. The speed changing also causes the direction to change. That's called refraction. Take a look at the picture that's on the board right now of the pencil. Pencil's in the water. Right? We've seen this a million times before. Stick a golf ball retriever in the water as well, you get the same effect. Okay, so much so that sometimes when you stick that golf ball retriever into the water to fish out the golf ball, you actually have a hard time picking up the golf ball because you go to stick it in, aim right at the golf ball, but yet the golf ball retriever seems to bend when it goes in there and just seems to be a hard time finding it, right? Why does it bend? Why does it appear to bend? Why does the pencil appear to bend here? Well, part of this pencil is inside the water, part of it's outside the water. The part of the pencil that's outside the water reflects light, and that light goes straight to our eyes. We see the pencil where it really is. But the part of the pencil that's inside the water also reflects light from the sun or from the light bulb, whatever it is that's above it. But when that light leaves the water, when it goes from the water to the air, it bends, it changes direction, just like this waveform here changed direction when it went into the swamp. Now, as a result of that light coming from the red part of the pencil here, as a result of that light bending, it tricks us into thinking the pencil is somewhere other than where it really is. We think it's where you see it right now, but it isn't. The light bent, and that tricked us into thinking that it was, again, somewhere where it really isn't. We got to define a term. It's called the index of refraction. We think of this, we think of index of refraction kind of on an everyday level as simply a number that tells us how much light bends, or how much any wave for that matter bends, but specifically for us in this context, how much light bends. The bigger the number, the more light bends. The smaller the number, the less light bends. I want you to think of it that way. But the strict definition of index of refraction is not how much light bends. Rather, the strict definition is a ratio. It's the ratio of the speed of light in a vacuum, which you guys know by now, done this enough time, has a value of 3.00 times 10 to the 8 meters per second. It's the speed of light in a vacuum as compared to the speed of light in medium X, or whatever medium it is that you're trying to find the index of refraction for. So we can write this as a mathematical relationship. We can say n, which is the index of refraction, is equal to c, which, as we know, is 3 times 10 to the 8 meters per second, divided by v. So nx for material x is going to be equal to c over v for material x, the speed of light in glass or air or water or whatever it is that you're trying to find the index of refraction for. Now, how is v going to compare to the value of c? Always. No trick here, guys. Always the same answer here. How is v going to compare to the value of c? Yep. Always going to be less. I said there's no exceptions. Well, there is kind of an exception. The speed of light in air is really, really close to the speed of light in a vacuum. To 3 digits, it's going to be the same value. If we went to more digits, it would still be less. But to 3 digits, it's going to be the same value. So okay, air would be the exception. Everything else is going to have a value that's lower than 3 times 10 to the 8, and that gives us an index of refraction that will always be 1 or greater. If you get an index of refraction in a problem that's 0.75, you're wrong. 0.99, you're wrong. The lowest it can be is 1, because the best you can do for the speed of light in something other than a vacuum is 3 times 10 to the 8, and that's in air, which gives you an index of refraction of 1. Otherwise, it's going to be a smaller number, and it's going to go up. The index of refraction of air is 1. The index of refraction of glass is about 1.5. That means that light in glass slows down to about 2 times 10 to the 8 meters per second, dramatically. Speed of light in a vacuum, in a diamond, well, the index of refraction of a diamond is about 2.4. Speed of light in diamonds slows down even more so, even more dramatically than it does in glass. And that's why diamonds sparkle so much. That's part of the reason why they're so valuable. They sparkle so much because of the high index of refraction. We'll talk a little bit more about that later on. Now, talk about the index of refraction as being a measure of how much light bends. The ratio of the speed of light in a vacuum to the speed of light in medium X. The index of refraction for every material is actually slightly different depending upon what color you're using. The index of refraction for glass, some certain type of glass for red light, maybe it's 1.499. Maybe for violet light, it's 1.501. It's not very much different, but it's different for each different color. Now remember, index of refraction is not a property of the color. It's not the index of refraction for red or for violet. It's the index of refraction for glass or for plastic or for whatever. It's just that the glass has a different index for each different color, slightly different for each different color. The bottom of the page here, you see a prism. It's made out of glass. It has an index of refraction of about 1.5, give or take a little bit. Over here is air, has an index of refraction of 1.00. It would actually be 1.000 something, but the 3 digits, still 1.00. Right here we've got white light. White light consists of all the colors of the rainbow. It's all of them together. That's the light that's coming from the sun. Red, orange, yellow, green, blue, indigo, and violet. It's all together. It just kind of looks whitish, yellowish when we see it combined. But watch what happens when that white light strikes the prism at an angle. White light bends, right? Every color bends, but every color bends a slightly different amount because there's a different index of refraction for glass for each different color. So what you're going to find here is that the light splits up. It disperses. Okay? Dispersion. Red light bends the least. Violet light bends the most. It happens again when it reaches the other side. Red light bends the least. Violet light bends the most. So what ends up happening? Well, the light that went in as white light, all the colors of the rainbow together, comes out as a rainbow. Red, orange, yellow, green, blue, indigo, and violet. Literally a rainbow. Dispersion is the process by which rainbows form. White light splits up because of a different index of refraction for each different color. Which one bends the most? Violet, high frequencies. Which one bends the least? Red light, low frequencies. So we would say that low frequencies would have, or glass would have the lowest index of refraction for low frequencies. Glass or any other material would have the highest index of refraction for high frequencies. And of course, wavelength would be the exact opposite effect. Make sense? Now, finally, I want to give you an equation that puts all this together mathematically. It's called Snell's Law. Snell's Law, you can see, has 4 different parts. It relates together the angle of incidence and refraction, the angle that it comes in and out of the boundary at, the speed, the wavelength, in the index of refraction, n. I want to go back here for a second. When the soldiers marched from the parking lot to the swamp, the speed changed. Why did the speed change? Well, because effectively n changed, right? The index of refraction changed. The material changed. It was pavement, and then it went to swamp. So because n changed, the index of refraction, the speed changed. Now, because speed changed, the wavelength and the angle changed. Take a look at the equation in Snell's Law. It has 4 variables: theta, v, lambda, and n. Because n changes, v changes. And because v changes, theta and lambda change. Now, one more thing. Let's take a look at the relationship between those variables. Okay, as you go from pavement to swamp, what happens to the index of refraction? Bigger or smaller? You're going from pavement to swamp, it's actually going to get bigger. Okay, so it's like going from air to glass. It gets bigger. Okay, and what happens as the index of refraction goes up? What happens to the speed of the wave, this soldier wave? What happened to the soldiers when they went into the swamp? They slow down. So as n goes up, v goes down. Take a look at lambda. As v goes down, lambda goes. Look at it. Here's lambda. Here's lambda. Lambda goes down. Now, it's a little bit hard to see from this diagram, but theta, the angle, would also go down. So as n goes up, the other variables go down. That explains why it's theta 1 over theta 2, v1 over v2, lambda 1 over lambda 2, n 2 over n1. As n goes up, the rest of them go down. As n goes down, the rest of them go up. N is inversely related to the rest of them. Therefore, they're all going to be 1 over 2. N is going to be 2 over 1. This is on your data sheet. But be careful. I can't tell you how many times people over the years just kind of get caught up in V1 over V2, lambda 1 over lambda 2, N1 over N2. Okay, even though it's right in front of them on the data sheet. N2 over N1. Looks like kind of a complicated equation, 4 parts to it. The good news is you're only ever going to need to use 2 parts. Use whichever 2 parts work best for you. Write down your givens, and then let's see which parts work for those givens. All right, let's do an example. This, by the way, before we do the example, just a table that shows us different indices of refraction. Notice one little thing at the top, though. It says the index of refraction for yellow light, sodium yellow light of that wavelength. Why did I specify that? Why don't they just say the index of refraction? Yeah. Yeah, it's different for each different color. So it'll be slightly different, not very much different, but slightly different for red and for violet. And yellow is right in the middle, right? Roy G. Biv, so pretty close to the middle. So they're using kind of an average index of refraction there. Most times on an exam, it doesn't actually say that. It just says, here's the index of refraction. You can assume that the index of refraction that's given to you is for the color that you're using. Does that make sense? Now, one more thing. They give all these to 3 digits except air and vacuum. On your data sheet, they tell you the index of refraction of air is 1.00. To 5 digits, it's not. But to 3 digits, it's the same as it is for a vacuum. All right, now let's take a look at that example. It says yellow light, which is what we had our data for, travels from water into crown glass. The light rays are incident on the crown glass and then go 35 degrees. So let's draw this out here before we get too far. This is water. This is crown glass. Let's say the index of refraction for water is 1.33. And the index of refraction for crown glass, you can see that there's differing values depending upon what kind of glass you have. 1.52. We're going to draw a normal line and measure our angle of incidence from the normal line. So this is my first ray. Okay, 35 degrees from the normal line. It's going into the crown glass. Now, it's going from an index of refraction that's low, 1.33, to a number that's high, 1.52. What's going to happen to the speed? As n goes up, v will go down. Good. As n goes up, v goes down. As v goes down, lambda goes down. As lambda goes down, theta goes down. That means it's going to bend which way? Going to bend this way or going to bend this way? Option 1 or option 2? N went up. V went down. Theta went down. It's going to be option 1, isn't it? Okay, theta 2 has to be smaller than theta 1. It's going to look like this. We're looking for theta 2, but we know it's got to be an angle that's smaller than 35 degrees because the speed went down because the index of refraction went up. So what do we got here? Well, we got Snell's law, sine theta 1 over sine theta 2 equals V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. Sine 35 degrees over sine theta 2 equals N2 1.52 over N1 1.33. Now let's rearrange this. Let's take this up. Let's take this up. Becomes 1.33 sine 35 equals 1.52 sine theta 2. Let's do this on the calculator. 1.33 times sine 35. Let's divide that by 1.52. Now, how do we get the theta 2 now? 0.5019 equals sine theta 2. How do you get theta 2? Yeah, the inverse sign. We're going to say second function sine of whatever we just got, 30.1 degrees. Is that smaller than 35? Probably did it right then, right? Probably did it right, because we know that theta 2 has got to be smaller because V is smaller. V is smaller because N is bigger. Got it? All right, let's take a look at these 4 questions, please. See if you can get those done in the next 4 or 5 minutes here. You might be able to, and that leaves you only with those other 2 bits of homework to do during scheduled help and for homework.